Alright guys, let's go ahead and do a little linear approximation. Having looked at the scheduling that she's given you, it doesn't look like she's getting into differentials at all, which is good for you because it's just one more thing. Rather underwhelming thing too. Here's what's the core of this section and why this section is actually important, despite the fact that sort of the methods involved within it are actually quite simple. Approximation winds up being a common theme that you're going to see as we move forward, and this is just the first of many instances that approximation allows us to, this method allows us to approximate things that otherwise, especially if you live in a day and age when you don't have a calculator, it allows us to get at a very, very close number to what it actually would be. So it not only helps us in terms of ballparking numbers, it does give us some sort of historical appreciation for those guys that lived before they had TI-84s. So let's go ahead and say, well, let's say I'm asked for the square root of 18. Well, the square root of 18, and I've taught you how to approximate this, at least, plus or minus 1/10 either way. It's obviously a little bit greater than 4. It's going to be less than 5, but square root of 18 is closer to square root of 16, and so it's probably 4.1, 4.2, somewhere around there. But let's say I want something a little bit better in terms of an approximation. Well, I know that this is close to root 16, okay? And I know root 16 is going to be 4. Now I can use that because I happen to know that if I take that and actually turn it into a function, take the operation that we're talking about, the square rooting, and actually entertain the function at the point 16, 4, I can actually get a tangent line to that function at that point. And let's go ahead and show us doing that. So we know that y prime is equal to 1 over 2 root x. And if I actually go ahead and evaluate that at 16, I get 1 over 2 times 4, or 1/8. So that allows me to, y minus 4 is equal to 1/8 x minus 16. That allows me to get a tangent line, y is equal to 1/8 x. If I distribute the 1/8, it's going to be minus 2. Minus 2, add 4 to both sides, is going to be plus 2. That is the equation of the tangent line to the y is equal to square root of x curve at the point 16, 4. Well, let's go ahead and see why that benefits us. So let's go ahead and pull up Grapher. Let's go ahead and do square root of x, and we'll change it into the hand and sort of drag it along here. And let's zoom out just a smidge so we can actually see all the way to 16. Now I need to go ahead and get a new equation, and I need to 1/8 x plus 2. And we see, let's go ahead and highlight both of them, and then let's drag it on over here to 16. If we actually zoom in right here at 16, that is where the point of tangency is. Over here at 18, because the square root function flattens out so fast, and because 18 is sufficiently close to 16, notice that it's very, very hard to actually distinguish between the values at 18 of the tangent line and of the curve. So we're going to use that to our benefit, okay? Let's actually zoom in once more if we can and actually see whether it actually gives us a better picture of it. So let's zoom in again. And we see way over here, this is the point of tangency over here at 16. At 18, look at that, I've zoomed in really far, and they are still just very, very close to each other in terms of their output. So what that means is that I can use the tangent line of a point sufficiently close in order to approximate that, because obviously plugging 18 into the square root function is really not that good of an option. But I can plug 18 into the tangent line problem. And if I do that, I'm going to get 18/8 or 9/4. 9/4, okay, is going to be what? Well, that's 2 1/4, 2.25. So that's 4.25. That is the approximate value that I have arrived at for the square root of 18. So let's go ahead and see exactly how close that is. Okay, and we'll just do the square root of 18. 4.242 or 243. That's extremely close, okay? It's extremely close to 4 1/4. And so we see that as long as we pick a point sufficiently close to find the tangent line at, then we're going to be okay. Now, if I do it for root 18, I'm not going to choose the tangent line at 25/5 because it's not going to be as good, okay? And I can actually show you that. Let's go ahead and reevaluate root 18, approximating from a different tangent line. Let's do y prime of 25, and I'm going to get 1 over 2 times 5 is 1/10. And of course, my equation of the tangent line is going to be at 25/5 and not 16/4, right? Farther away from 18. So I get y minus 5 is equal to 1/10 x minus 25, or y is equal to 1/10 x. Now when I distribute the 1/10, right, that's going to give me 25 over 10. That's going to be 5 halves, and if I'm going to subtract 5 halves and then add 5 to both sides, it's going to be plus 5 halves. Okay, well let's evaluate this one at 18, and I'm going to get 9/5 plus 5 halves. Well, let's go ahead and turn that back into 18/10, and let's go ahead and turn this into 25/10, and that's going to wind up being 43/10 or 4.3. Now, it's still not a bad approximation, but notice that the approximation from the tangent line at 25/5 is not as close as the tangent line value that I get for 18 at a point that is closer to 18, at a point 16/4, okay? So the whole idea is to identify the operation that's being done, find that function and evaluate a tangent line, find the equation of a tangent line to a point sufficiently close, and then evaluate. Okay, well let's do it with another root. Let's say that I'm given the cube root of 60. Well, I know that that is close to the cube root of 64, which as I know is 4. So let's go ahead and evaluate the cube root of x, and we'll get the equation of the tangent line at 64, 4. Okay, well that winds up being, y prime is equal to 1/3 x to the negative 2/3, or 1 over 3 times the cube root of x squared, right? And that, if I want to evaluate that at 64, is going to be 1 over 3 times, well, the cube root of 64 is 4, squared is 16, and so y prime of 64 is going to be 1/48. Very shallow slope, okay? And so y minus 4 is equal to 1 over 48 times x minus 64, and that gives me y is equal to 1/48 x minus, well, 64 is 4 times 16. That is going to be 3 times 16, so that winds up being 4/3 minus 4/3, but then I'm going to add 4 to both sides, so that's going to wind up being, that's 4/3, that's 12/3, so I'm going to wind up with 8/3, so y is equal to 1 over 48x plus 8/3. That is the tangent line to this function at this point. Now, that point is sufficiently close to, right? Because here's the thing, I'm going to use because this is close to 60 question mark, right? And it's that question mark that I'm actually trying to answer. 60 question mark. I'm looking for the value of this function evaluated at an input of 60. So since 60 and 64 are sufficiently close to each other, I'm going to go ahead and I'm going to evaluate this tangent line at 60. And that's going to give me 60 over 48, which is 30 over 24. And, oh gosh, I mean, they're both divisible by 12, so that's actually 5/4. So 5/4 plus 8/3, and you can get a common denominator and stuff like that. But let's actually just deal with it like this, okay? So that's 1.25 plus 8 divided by 3, and that winds up being 3.91, and then 6 repeating. Well, let's go ahead and let's look for the cube root of 60. That is really close, okay? And we've used the tangent line to evaluate that, okay? I mean, those are only 0.02 off. And that has to do with the fact that, as fast as the square root function flattens out and becomes almost linear, the cube root function does it even faster. And the farther and farther you go out in the positive x, the flatter and flatter it gets. So the better and better that a linear approximation is actually going to help you. Okay? Well, we've done 2 with roots. Let's go ahead and do something that's actually, I don't know, a little bit more difficult. Oh, by the way, I did a couple of these when I did the Skype session with Ricky this past Saturday. He told me that he was recording it, so as long as the recording actually didn't fail, he should have that for you. So that will be a couple more examples. Let's say I want an approximation for arctan 1.1. Okay, now that's obviously close to, okay, arctan of 1. Okay, so we're going to entertain y is equal to arctan x, and we're going to be looking for the equation of the tangent line at 1. Well, arctan of 1 is, anybody? Pi over 4, okay? And so obviously arctan of 1.1 is going to be close to pi over 4, which as you should know is a little bit more than 3/4, right? Because pi is a little bit more than 3, so a little bit more than 3/4. Well, let's go ahead and take the derivative. Y prime is 1 over 1 plus x squared, okay? Now I see the fact that I'm going to go ahead and get the tangent line here. That means I evaluate this derivative at 1, which gives me 1/2. And therefore I have y minus pi over 4 is equal to 1/2 x minus 1. Or y is equal to 1/2 x minus 1/2 plus pi over 4. And of course, I mean, I guess you could simplify those by putting them together. I guess that's, 1/2 x plus pi minus 2 over 4, or something like that, okay? Now what I need to do is I need to evaluate the tangent line at 1.1. Now, of course, once you get to this and it becomes this complicated, you need a calculator anyway, right? And so the charm of it kind of wears off in terms of being a good way of figuring something out that would have actually been, something that they would have done back in the day. But practicing the method and coming to grips with not only the utility but the power of approximation methods, that still sort of rings true. And you know how much I absolutely love decimals, so I'm going to change that into a fraction. And I'm going to get 11 over 20, okay, 11 over 20 minus pi minus 2 over 4, okay, and that is going to be 1.264. Now I am in radians. That's a wonderful thing about the new color one. It tells you right there what mode you're in. So let's go ahead and do arctan of 1.1. Ew. Maybe I messed up somewhere. Did I mess up somewhere? Oh yeah, I did. I should have added this right here. That was actually a plus sign. So let's go back up. And let me go back to here. Okay, yeah, there we go. So it's the last two. This is the actual value, and this is the approximate value. And they're only apart by, less than 3 thousandths. Okay. Now, we can go ahead and, if we want to, go ahead and do inverse tan of x, and then, of course, the 0.5x plus pi minus 2 over 4, and then we'll go ahead and graph that. And there's the arctan, and remember, because it has that asymptote at pi over 2, it flattens out very, very fast. That is our tangent line problem that is our tangent line right there. Let's go ahead and change the window to go ahead and give us, an x max of 5, and then a y max of, I don't know, let's do 3. And so there is a better scaling of the arctan for our purposes. And here comes the tangent line. And so, of course, 1.1, and this goes all the way to 5, right? 1.1 is going to be very, very close, and that's why. We can go ahead and zoom in just a little bit more. Let's go 0 to 2. There's the arctan. And of course, if that's 0, that's 1, and 2 is over here. Notice how close it's going to be at 1.1. That's why it's such a great approximation, because I've chosen a value of arctan that I knew. Right? Arctan 1 is capable of being evaluated, and you should know it like off the top of your head. That's why this works so well. Okay? And so I hope that helps, guys. That is basically the gist of linear approximation. Now, there are some different iterations on how those questions can be asked, but basically it winds up being finding a tangent line sufficiently close and evaluating how good your approximation is. Okay? I see from the schedule that has been given that the test is on Wednesday. Based upon if Ricky's recording didn't go through or something like that, or you have a specific question, please go ahead and email me. I don't see any reason to belabor the point. It actually is rather straightforward, and I doubt she's going to inundate you and bludgeon you with an insane amount of problems that deal with really obscure values in terms of linear approximation. So go ahead and shoot me an email if you need anything more on this. Otherwise, good luck on the test, and I will talk to you soon.